So today we will talk about two main topics: managing the threats and signaling. Right. So the first thing to talk about is threading. Right. So the first question is, why do we want to do multi-threaded? Why do we want to build our program to be multi-threaded? What's the benefit of multi-threading? Concurrency. So what does concurrency give you? Better performance, right? It's as simple as that. For most of the time, if you want to buy or upgrade a computer, what's this for? Why do you need a new computer? CPU. Better CPU. Your old computer doesn't work well as well, right? Modern programs demand basically more resources, and your old computer doesn't have enough resource to run all of them, right? So in many cases, your new CPU might have more CPU core, right? So if I write, basically, if I write a normal C program, single-threaded C program, am I going to actually get the benefit of having multi-core CPU on your machine? Not really, right? Because they're going to pick a core and run on that one single core, right? So a classic method to solve this is to do multi-threading, right? So inside a program, in order to actually do multi-threading, you need to make sure at least your program can run things in parallel, because that's one of the most important goals. Basically, if I want to write a parallel program, they better be able to run in parallel, right? So the program structure should express some logically concurrent tasks. They also should be responsive, right? When I said that, it basically means that I want to be able to shift some of the work and run them in the background. All right. And then what I want from it is performance, right? I want to be able to exploit multiple processors. I want to be able to manage IO devices well. I want to do this and I want to do it well. All right. So let's give one example, right? How many people use a map application nowadays? Everyone. Basically, if you want to navigate where to get from one place to another in Bangkok, you probably won't have to rely on a map application. Are they going to give a good direction? That depends. I've been directed to go into a really small like soy before, and I almost never be able to make it out of that because it's so narrow. But think about the map application. What are the different tasks that you have to do? Right? Obviously, you have to deal with data. You have to be able to pull the data on, first of all, where is your current position? Where, based on your position, where are the different things that you have to draw on the map? Because that's going to be based on your current position. Then there's going to be a bunch of other threads, right, that are spawned to draw the whole map here, right? As you can see, this thing shows an entire map, right? So let's say, I mean, drawing this thing might take a while, right? Because I need to draw a section of this. So my first question for you guys is, then can I split this map into, say, 4 regions and have each thread draw one of the corners? Yeah, right? As long as I know where I am, as long as I have the collection of the data about the surrounding objects, I can draw a smaller portion of the map and then stitch them together afterwards, right? And will that make your rendering faster? Yeah, because now each thread do fewer amount of work, all right? I have to draw fewer things, right? So the abstraction, the thread abstraction is basically, let's say you have a single threaded execution, right? It's a sequence of tasks. When you say threading, think of it as a task. You spawn a task to get something done, right? And it's a single execution sequence that represents a separately schedulable task What do I mean by separately schedulable tasks? It means that let's say I have a magic scheduler. Think of the computer as like a factory, right? And I have a manager. I can tell the worker to perform each task in some scheduling, using some scheduling. Say, hey, you go do this, you go do this. And single thread. Each of these single thread is basically a sequence of instruction. When I said a sequence of instruction, think back assembly that you've seen in system skill, right? These are basically becomes an assembly file that will run from the first line, second line, third line, fourth line from that like simple model. Now you have multiple tasks spawned into multiple threads. Each thread has simple single execution sequence. Then when I have each task, right, OS can say, hey, this should run here, this should run there, because in reality, right? So this is a programmer abstraction. When you write a program, you can say, I want my program to spawn 1,000 threads, if you will. I mean, if you want to, you can keep spawning more threads, right? Each of these threads will be assumed that they'll be running on a processor, because that's your brain. If you want to do something, you have to do it through your brain. So that has to be a processor that takes a thread and run it, right? What's the problem with that abstraction? How many core does your CPU have? 4. Anyone rich? I think I've seen 8 core from you guys before, right? If you are looking at the server, maybe 16, 32 core. If you look at Cisco server, it's a poor man's server. It's like 2 core. That's why it's so slow. I mean, we don't have a lot of budget. Well, 2 is better than 0, right? That's what we have right now. Yeah, I mean, the service share among many other things that we have to run. So we basically spawn a virtual machine. It's a Linux VM that would run your Cisco server, right? So that's why we just dedicate 2 core for you guys, because we know that you don't do a lot of the most complex thing you run there is VS Code, an infinite loop, and some memory leaking application that eats the entire memory. I've seen that as well. But yeah, so that's a programmer abstraction. In reality, you don't have a lot of CPU core, right? So you have to deal with that. Who is the person responsible to deal with it? Huh? The OS. Because again, think of the OS as kind of like, this is the thought-like entity in your machine. Your hardware, think of hardware as just the earth, right? It doesn't do anything. Then, well, I'm not Christian, so I might have the wrong analogy. But let's say, imagine a God, right? That comes in and you go here, you go here, you go here. God assigned the task. That's the OS. So it has a bunch of these threads that say, hey, I want to run this task, right? The OS would make sure, right, that these tasks are assigned to the CPU. So to be honest, there's many things you can play around in terms of scheduling. Why? You are working on multiple types of devices, right? Your laptop is going to look different from your phone. Your laptop or even iPad, right, might be running multiple things in parallel. How many people play games on Steam with some other app like Chrome open and things like that? We do that a lot in our desktop, in our laptop, right? We don't do that in a phone. So the scaling for the OS would have to change to adapt to like the new particular resource constraints that each hardware is provided to, right? And threads are run at an unpredictable and variable speed. So let's say this is a programmer view of, this is your program. Think of it as this is your program, right? Now let's say I spawn another thread, right? The actual reality is maybe my OS would just say, hey, run the first line, followed by the second line, followed by the third line. See, this is a possible execution number 1. I run the 3 lines together. Another possible execution, I run the first line, the OS say, hey, you stop running, I'll run something else. That's possible. Some other threads come in, and that new thread run whatever they have to run to switch back, right? This is another possible execution. I run 2 lines, right? Switch by another thread, right? And this happens a lot in your computer, right? Another example of this, how many of you heard of the Intel hyper-threading technology or hardware multi-threading? Right. So many of you haven't heard about it, but think about it this way, right? To switch between one thread to another, remember those PCB, right? The process control, all those things that have the information, including the what is in my register and all those things. If I'm switching the thread, how many register file does my CPU have? Let's say I have an Intel CPU, right? Your abstraction would be I have 1 register file for whatever is running on the CPU right now. All right. I mean, why do I need 10? Because I'm running 1, so I will just build the hardware for 1. I don't have to build the transistor for multiple of them. We'll go into more detail in the architecture side of this class on, we actually have more for the purpose of performance, but it's for that one thread. Now, I said another thread can switch in. This is the same CPU. What happened to my register file? I have to save it, right? Because I have only 1 copy. So I have to basically I have to save that progress to make sure that the register file on the CPU gets switched to the new thread. So the new thread can run whatever program they have to run. Then you switch back, you do another copy. When I said copying, where is the location of my copying? Where do I copy to? I have the register file, right? And I can store something. I have the cache, I have the memory. So when can the OS access the cache? Not really, right? Because cache is not software managed. It means that my OS doesn't have access to the cache. So where is the closest place can I store this register content that I am not going to run right now? The memory. So context switching, this process to context switch, that's going to take a long time because I have to store a lot of things in memory just to make sure I can resume, right? It's like when you're playing a game and when you have to save your progress, right? Open up the menu, hit save game, and then select the save slot. That takes a long time. It's not like you can quick save all the time, right? How many quick save slots can you have in most games? Oh my God, your games are new. Used to be 1, all right? Yeah, used to be 1. Back in the day, if I want to do a quick save when I play a game, I hit like F5, if you remember, F5 or F6, right? To do a quick save and I keep playing. Hardware context switch is kind of like that. I have a spare register file on the side. I have a thread 1 and thread 2 active, but only one of them are running. When I want to switch the thread, I don't have to save that to the memory. I switch to another thread, and then I can switch back. So that's why in some of the specific, like if you buy a CPU, for example, right, you might have seen that it will say I have 4 core, but I can run 8 threads. What do they mean? I have 4 core, and mean I can only run 4 things at a time. But somehow it says I support 8 threads because they have hardware multi-threading. Basically, the other 4 threads are there on the CPU. They are not active. The CPU only runs this 4 threads actively. But let's say I have to go access the memory. That's going to take some time. Let's say this instruction, right? Access memory. What would be the logical thing the CPU would do? Switch to this thread that can run right now. Then switch back when my data arrives, right? So these are hardware multi-threading, but the concept is the same. I have multiple threads. They can get run at any point in time. These can interleave in any order as long as what? As long as within the same thread, I follow this order. That's the requirement. when I run this program, the program that I'm writing, it should be the first line that get run is x equal x plus 1, followed by y equal y plus x, followed by z equals x plus 5y. It can get run at any point in time. I just need to follow that order. If I don't follow at that order, what happens? The OS or the hardware is buggy, right? I write a code, I write a program, it doesn't follow what I'm writing. What, right? Basically, that's a bug somewhere. So again, the core concept here is the thread would run at any unpredictable and variable speed depending on the scheduling policy, right? Your application has priority. Let's say you have 16 threads that you want to run, you have 4 core, you have to pick who to run first. So the OS would look at the scaling policy, look at the priority and see who get to run. To make sure, again, actually, what's the main goal? What's one of the main goal of this scheduling mechanism? Huh? Speed things up. That's one goal. The second goal is it should make sure the user never notice that you're running 16 threads with 4 core, right? Your user never realized that. I mean, how many people have the old like iPhone 5 or 6 where it's only a single core CPU back in the day? As a user, they did not notice that, right? They are doing a good job at hiding the fact that it's only one CPU, handling everything. So that's one of the tasks, right? And no thread gets slowed down way too much, right? Let's say I have 16 threads. If 15 of them is really fast and one of them never get to go, that's a bad policy as well. You might want to be fair, right? So there's multiple things that we cover in the first lecture about the job of the OS. Second lecture, we cover the job of the OS. What are the goals, right? And here's more of a visualization. I can have 3 threads right now. I can maybe run 3 of them in parallel if I have 3 CPU core. And let's assume that three of these threads doesn't have any dependency or any synchronization. We learn about synchronization on Thursday. Basically, let's assume that this 3 thread can fully run in parallel. It means that I can do this. I just run 3 of them in parallel. When will this happen? Anyone have an idea? Yes. Yeah, thread 2 might depend on thread 1 finishing. Thread 3 might depend on thread 2 finishing. That is possible scenario, right? In that case, I cannot run thread 2 before thread 1. Remember the wait thing that we have earlier, they have like from last week. Wait means that the parent will wait for the child thread to finish, right? So another possible scenario, it might be fully parallelizable, but you only have one CPU. Only one CPU is available, so I have to run each of them back up like one after another, right? Because I don't have the resource to run. This is also possible. One possible example, right? Let's say both 3 threads want to modify a counter. This is shared among the 3 threads, right? If I want to do counter plus plus, when I do counter plus plus, what are the operations you have to do? When you want to increment something, the first thing you have to do, read the content, then overwrite it, like do the add, then overwrite it. If you think about this, like read, increment. In modern data, this thing is pretty atomic. Atomic means that nothing can come in the middle of that process. But let's say I want thread 1 to increment at the same time thread 2 and at the same time thread 3, right? If I don't control anything, there might be a chance that you get a buggy data. Why? Let's say both of the thread read, yes. Yeah. you have what we call a rest condition, which we're gonna cover in the next lecture. But the gist of it is, let's say thread 1 and thread 2 both happen to read the data at the same time, which is okay. I read counter, it say 4. Then I proceed to increment from 4 to 5. Both threads will increment from 4 to 5 and say, hey, I'm gonna write the new value 5 to this variable. In that case, that's a bug, right? Because it's supposed to be 6, not 5. So one thing you have to do is, for example, you can lock the counter to make sure that if thread 1 is modifying it, no one else can access. So you can have this kind of thing. I occupy the resource, no one else can run in parallel because I'm occupying the resource that people need it, right? So this is another model. Basically, this can also be just context switched by the OS as well. Nothing wrong with the thread, nothing wrong with the parallel. They are fully parallel, but the OS come in and say, hey, stop running, run this thread because something important needs to happen, right? So now that we learn about threading, right? Let's transition into how do we use it. All right, how do we use it? So we can use the thread API. These are available in C. For example, we can do thread create. Thread create is different from forking. Remember, forking is what? Spawn child process. Process and thread are not the same. A child process doesn't really share anything with the parent, except the code looks the same. Thread processes have a lot of shared data. We'll cover that next in the next lecture, but the gist of it is different. Thread, you can have multiple threads as a part of the process. One process can contain many threads. So when you do thread create, it creates a thread, store the information related to the thread, and then you can execute the function, right? To see how when you do thread create, you have the function and the argument in there as well. It basically allows you to say, hey, call this function, run them in another thread. Thread yield means this. Instead of letting them run in parallel, say, hey, stop. Give up the process. Like the thread that hit this function call, when you hit the thread yield, I stop using the processor. And let some other thread run. Then the scheduler can resume whenever the calling thread, like basically when the scheduler thinks that, hey, it's time to get scheduled again, it would run. So that when things will get run again depends on the implementation and how you schedule things, depends on the OS as well, right? Then you have thread join, yes. Just that, because I mean, you don't really, the purpose of thread yield is like, I want to stop running, right? So it doesn't really need any arguments there. It can be a part of like one of the line in the code. I finish running a function, I yield the CPU. Thread join is, let's say you have to wait for a thread to finish, right? You spawn multiple threads. Some of them finish. Let's say this is like your program. Your program happened to spawn thread 1, thread 2, and thread 3, right? At some point, when they are all done, you need to resume the progress and keep going, right? But the thing is, how can you have, like, you need to make sure that that's a function call in C language that you can make sure when thread 1, thread 2, when in this case, thread 1 and 2 are done, wait until everyone else finish before you keep going. That's the join. Join means that in this case, right, it waits until the thread that you're waiting finish. Then you put in the thread inside the argument saying, I'm going to join this thread and this thread. So in this case, you can basically, for example, join thread 1 and thread 2. Join thread 1 and thread 2 means that, let's say in this case, thread 2 finish first, right? Then it will wait for thread 1 that it merge. So for each thread, you can only called join one. Why? Well, after the merge, it's gone, right? So that's why when you spawn a thread, you can only join once. If you join multiple times, that's going to be an issue, some error, right? Basically, it won't run. Then thread exit. Thread exit means I'm going to finish the current thread. Then you store the value you put in here, the return value, in the current that is exiting. I store that in the data structure. If I have another thread waiting for this exiting thread through a join, for example, right? It means that, well, the exiting thread will not, well, it exits, it doesn't finish. So in that case, I can resume the waiting thread because it's done. Here's what I mean. Basically, let's say I have thread 1 and thread 2, right? And then there's a join here. Basically, it means I'm waiting for thread 2, right? But let's say over here, thread 2 call exit. Do I have to wait until the end of that arrow, or can I just resume right now? Yeah, I can just resume execution at this point. I don't have to wait here because thread 2 already exit. Right? There's no need to wait until thread 2 finish the whole thing. All right, so here's an example, right? How should we do this? Okay, how about this? I'll leave this on the screen so they can parse this a little bit, and we'll go through what happened. Basically, if you run the code to the left, the right side is one of the samples that will get print on your screen. In this case, what we're doing is we spawn a bunch of threads. Each thread returns something, and you see that it gets printed, right? So let's pause here quickly, right? Let's do a 5 minutes break. All right, I'll keep the slides up here. You can check the slides in the meantime during the break. I'm gonna circle the parts that are relevant so you can take a look at that. All right. Yes. Yeah. Huh? Yeah, I'll try. So give me a second. All right, so we now talk about this example, right? And you see how we can do thread create. And thread create, first of all, right, it takes the thread as an input. This is a function you want to run. This is the argument for this function, right? The argument I will go into the input inside function called go. Inside function called go, basically the only thing it does is say hello from thread ID, print that out, return 100 plus n, right? So over here you see the thread hello will spawn 10 threads from thread 0 to thread 9. Thread 0 to thread 9. And then inside, these are the inside the function go. And inside them say, hey, thread 0 return 100. Oh, my bad. Sorry. It inside the function code print hello from yes. It's from the function go, which print just hello from thread 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then it exit. It exit with a code 100 from 100 plus n. Then when you have thread join, right? Thread join, it takes in the exit value. It takes in the exit value. And remember, each thread can join once. Once you join, you're done. Right over here, so when I have thread join, I have a loop, right? See how I have a loop here. How many times am I looping? To the number of threads, which is 10, right? So I will basically do thread join for each of the threads. In this case, thread I is going to be replaced by 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 inside this loop. And when it exits, it prints thread ID, return with the return value, which is 100 plus the ID. And then afterwards, it main thread done, right? And as you can see here, right, hello from thread 0, and then thread 0 return 100. The order, as you can see here, the order can happen in any order. Thread 0, see here, it's finished first, while the hello from thread 3, 4 is not even done. And look at this. Anyone notice about the order that is not sorted by the number, even though inside my loop, I spawn a thread in order. So thread 0 gets spawned first by then 1, then 2, then 3, then 4. It just happened that thread 5 gets scheduled first. Then thread 2, then thread 6, then thread 8, then thread 7, then thread 9, right? And then they exit. What's the next thing that you notice? How about the order of thread return? Yes, in order. Why? Because you have the main thread, right? The main thread is the one in the main function that are looping. The main thread are looping, and inside them, right? I have the loop from 0 to what? So what's the first thread is gonna wait until it's finished? 0. So that's why the thread ID return number will be printed in order, because the main thread is not run in parallel. That loop is sequentially done. So it first join thread 0, then join thread 1, and join thread 2, then join thread 3, 4, 5, 6, 7, 8, 9. That's why you see the order in there. Then you do main thread done. Inside thread create. Once you call thread create, they're gone. They keep running. That's why inside the hello from thread can be in any order, but outside of this, the main thread will still run things in order. All right. Okay. So we have already we have a question. What do I mean by thread context? Because I use this word already, right? When I said thread context, it's the state of the thread, which include things like thread control block. It's similar to the PCB, but now it's for the thread, right? And thread also has the stack. So they share the code, right? Obviously, because you spawn a thread within a program, they share the same code with the main process. They also share the global variable. Why? Because when you do thread create, your input is a function you're calling and the argument for the function. The global variable is defined outside of the function, so it has the shared global variable, and it also has a shared heap because it's the same process. So the shared state, again, there's a code, global variable, and heap. All right. And inside each of the thread, you have your own stack information. You have your own register that you have to save and store and operate, because these are separate tasks. These are separate function calls, so they better use different register, right? The different set of register, and then some meta. Like when I said metadata, basically it's a part of the data that are not related to the data for your program, but it's related to the management. In this case, it's your thread, right? How many people here take, yes? The thread. Think of it this way. How many people have a camera and have been looked at like information that's stored in a file when you take from camera? Okay, so let's say anyone know this format called RAW? These are like full-blown information that includes things like what's my camera aperture, camera setup, what's the ISO, and all those things. Because you can actually look at and study how did I take this particular picture, right? That is a part of the metadata. It's not a part of your picture. It's not the data related to your picture. It's related to the instant when I capture that picture, right? If I take it out, it doesn't matter. My data will be the same. Same here. if I take the metadata out, will my thread run? Yeah. Will it be as efficient as with my metadata? Probably not. It is extra information I can add in. And it depends on the OS design on what do I want to add in to make sure these are more efficient. And the life cycle, this is something that you might see and think this looks like a process, because to some extent it does. You spawn a task, you run them, right? So when you create a thread, you initialize them, it becomes ready, then the OS comes in and run them, right? So when the schedule resumes the thread, it runs. When it's running, you can yield, you can join, you can also get kicked out by the OS, right? And then that becomes ready again, because I mean, I got kicked out or I stop running, and I keep running until I have thread exit. All right. So, my bad. So the way you implement threading, right? There are multiple ways you can do this. You can use kernel thread. Here, the top box is the kernel. The bottom box is the user. Basically, user cannot touch the kernel, but the kernel see everything. All right. Now, some kernels are multi-threaded. Some kernels are multi-threaded. Sometimes you have to have some long-running management tasks to manage your hardware. Right. We're not going to go into way too much detail into what are these things. Internally, your OS basically run a few different threads to make sure your hardware operates. Things like, for example, updating the page table, spawn another table in the page table when someone calls malloc, and you have to like basically manage virtual memory, manage the scheduling, try to figure out what are the programs that are running. Are there any attack by someone else? Can I detect any attack so like maybe I can stop running, reboot a computer because someone attacked my computer, things like that, right? These also can be scary. Think of kernel thread the same way as the threading we've seen so far, right? They have the share code, global, and heap. Each one of them has their own stack, right? These are kernel threads. These are different processes. So the kernel thread would have the TCB, the thread control block. The process has process control block. So this is basically, let's say this is process 1, this is process 2, this can be like process 3. In this case, process 3 has 3 internal threads inside the kernel thread, right? Then user level process can also have its own process and the thread inside them as well. So to implement user level thread, at the end of the day, right? At the end of the day, someone has to write that code, right? And if you have the kernel support, you can have a one-to-one model. Each user thread is mapped to a kernel thread. It's as simple as that. When I spawn a user thread, I pair that up with a kernel thread and then let them run. P-thread stand for POSIX thread. POSIX is a standard. It's a standard API that's understood by multiple OS. That's how I can write the same function in C language, but should work across different OS. Because someone defined that, hey, let's use the standard as the function call will be named this way. The assumption when you call the function should behave this way. This would allow me to run the same POSIX threads on Linux, Mac OS, and many other OS, right? So pthread is actually used in many places. When I spawn another thread using the pthread command, this is different from thread create you saw earlier. This is like POSIX thread API. It will map that thread with the kernel thread and it will just run. You can have the threading model without the kernel support. Sometimes we call this M21 model, sometimes we call it green model, which is like more lightweight. I have one single kernel thread. I will have to manage multiple user level threats. I can have a hybrid model, which is M to M, M by M model, multiple user threat, my bad. Multiple user threats can be backed by multiple kernel threats. So for the one-to-one model, right? Most operations are system call. Kernel basically now have full control over the scheduling because kernel is the one that implements scheduling and the mapping is one-to-one. So each kernel thread is one user thread. So now I have full control over scheduling. When I have an interrupt or making a syscall, I don't block. That thread is not blocked. And the model, as you can see here, right? I have the kernel thread here, will map to user thread, which get mapped here. So that's one model. The next model is many to one. Sometimes we call it lightweight or green thread. So eventlet, greenlet, G event. Kernel support is not needed. And kernel is not aware, hey, there's multi-threaded program going on. Kernel just keep running. I have one single kernel thread that on a side basically handle this. User level library. This is where things get easier for programmer. These are basically user level library that you can call that is responsible for scheduling. So I don't have the kernel responsible for scheduling. Kernel thread means that the kernel or the OS handles scheduling. Here, I have this user level library act as if it you say I spawn one kernel thread to handle this library. But internally, they are hiding the fact that this library has multi-threading going on inside the library that has their own scheduler to pick who get to run when. It's all built inside the user level library. And the syscall, but the thing is, when you have a syscall interrupt, like someone hit the keyboard, someone moves the mouse, these are in the user land, so that would block the thread. It blocked the thread because now user thread that are mapped to this one single kernel thread is now blocked because these are on the user level. And again, the model is you have one kernel thread that manage a bunch of these user threads inside the user level library. Think of it as you write your own user software that spawn your own version of threading. Inside, internally, I have my own scheduling that can control everything. But because user have lower priority than kernel, if kernel has things like system call or interrupt, I have to stop. Many to many, yes. Yeah, so inside here, scheduling is done by the user software. The library itself have to basically define how do I schedule them. Oh, like the user get like real setting. Okay, so the question is, do I get parallelism out of this? Yes. Because I mean, I can run multiple user level threads, right? At the end of the day. But now I port the scheduling to the user API. So having like one kernel thread. Yeah, basically these are basically run and all share this one kernel thread, which inside the kernel thread they have their only one stack and one set of register file to handle kernel thread. But the thing is, because most of the management is done in the user, unlike the one-to-one where a lot of management is done in the kernel because you have to schedule by the kernel. Over here, most of the things you have to run is in the software code. So context switching and all those things is handled by the user API. It's only one kernel thread that have to run this. Many to many is basically I have multiple kernel threads that are backed by multiple kernel multiple kernel threads backing multiple user level threads. And the thread library, again, the thread library control the user level thread, but it multiplexes across different kernel threads. Basically, think of the many-to one, the user level thread, but now I can use multiple kernel threads to control this. When I said multiplex, it means that maybe this kernel will be mapped to this guy and this guy, this kernel mapped to this guy, and this kernel mapped to this guy. Now it allows you to multiplex across different user level threads. You can also have implicit threading like asynchronous I/O, event-driven programming, where you have single-threaded program code with a high-latency I/O devices. You have thread pool. You will see this again at some point. We're not gonna talk about it here, but you have asynchronous worker. You don't have to like synchronize the new thread join. You have async await. In fun horror, you have fun with this topic. Code routine as well, and you can also have this like Grand Central Dispatch. So these are concepts that we're not gonna cover in this particular course, but it's been implemented, it's been used, and these are something you can look at. Or if you have any questions, ask follow-up question on Discord. So follow this up. All right. So again, we're gonna switch topic to signal. It should be about 10 or 15 slides. And it talks about how can hardware communicate with stuff. Yes. Yes, question. Oh, okay. So do we need 5 minutes break before we resume, or should we keep going? Yes. The signal slide. Oh, the signal slides. It's not in PDF. On. It's gone. Oh, okay. Let me fix it. Signal. Basically the concept is I want to be able to send messages that would notify my process that some event happened. Some event happened. It's as simple as that. All right. Think of it as exception and interrupt. For example, if you divide by 0, I can cause the divide by 0 exception, notifying the program, hey, someone is trying to divide by 0. I don't know what to do with it because it's not defined mathematically. Similar thing. Signal has an ID tag to that. Many of them has a name, actually, even the name tag to it, right? You guys close the process in C when you're doing sysctl, right? Somehow you have to stop a process. How do you do that? Control C, right? That would stop the running process. Basically, when you do Control C from keyboard, the computer generates a signal called sigint interrupt to terminate the running process, right? When you do the command kill, for example, kill with the process ID would send the sigkill command to the process, say, hey, go die, to actually kill the process, all right? And only information in the signal is just the ID, and that it arrives is as simple as that, right? Why do we want this to be simple? Because we want to make sure this is as simple as possible for the OS and the hardware to handle. If something happened, here's the ID of the signal that happened, take care of it. To send a signal, right? I have to have a destination, right? Basically, if I want to send a signal to someone, I need to know where am I sending a signal to, right? And to do this, the kernel, right? The kernel basically has to update the state in the context of the destination. So you have a process that are running. The process has the context about, okay, here is the state of my program that I'm running right now. When I have a signal, the kernel basically go there, sneak into the context information, say, I'm going to update you that some signal is there. The process receives it. Some of the reason, for example, the kernel can detect system events such as I have divide by 0, right? Or termination of shell. FTA, signal that floating point error, divide by 0, I don't know what to do. Your shell process terminate. I'm sending a signal, say, hey, your shell process terminate. If you're waiting, for example, you can now go. Another process can kill someone else by sending a syscall called sigkill. Sigkill will kill another process. It basically explicitly requests the kernel, basically it requires the kernel to send a signal to the destination to terminate itself. When you receive a signal, right, it is forced. Once you got a signal, the kernel forced you to react. And there are three possible things you can do. You can ignore. I got a signal, I do nothing. I can terminate the process. I got a signal, I can queue the process, and I can have an option of pumping out whatever I have right now. We call core dump. Dump the content of the core that are running the process right now. That's why we call it core dump. The CPU core is running something on that process. I dump the content out so I can debug later. I can catch the signal and use a signal handler. A signal handler means that I will have my own user level function that will get run whenever I see this certain signal. This is similar to exception handler. Like if I see divide by 0, I will do this, like try catch. Same thing, same concept. If I see this signal number, I will run this function. There's also this concept of pending signal. Pending signal is something that's sent but is not received by the user process yet. It's sent from the kernel. The user process isn't aware that it's there yet. It's not received. Why is that possible? Well, there can be at most one signal of each type going on at the same time, right? One per type at the same time, and they're not queued. They're not being queued up. So let's say a process has a pending signal of type K. Any subsequent signal of type K is going to be thrown away. Because I just have to handle that one yet. I don't have to buffer to store. It's only one variable in my process context for that signal. If I update it, it just receive. If I have more signal of the same type coming into that process, nothing will happen because that variable is already received, so it will get thrown away. I don't have to spam Control C. Yes, that means you don't have to spam Control C. When you if it's a different type of signal, basically the process context is aware of the two signals. It will handle both of them. Depending on how the handler is defined, you can also, I guess you can also ignore and terminate. Depending on the signal number. If you got 6 kills, most of the time you terminate. Right? Per IG. Per IG. A process can also block the receipt of the certain signal. Block signal can be delivered, but not received until you unblock it. Basically, when I block the signal, it means that that type will not arrive here. Even though someone sends me the signal, I will not receive it. It's different from pending. Pending means the signal is sent, process is not aware, it might be handling them later. Block means I'm not going to take this signal. Pending signal is received at most once. And here is the more like the diagram that illustrate what happened. So each process belongs to exactly one process group, right? So you have the process ID and the process group ID. The process ID and process group ID. So when you have a shell, right, it has a foreground job, which, I mean, the foreground job can spawn a child process as well, depending on what program you're running. You can also have a background job, job 1 and job 2. Quick note, this is your lab one. Make sure your shell is functioning that way, right? It can maintain like process ID, process group ID. In this case, right? For example, the foreground job has group ID of 20. So the shell processes, which have process ID 21 and 22, might have the same group ID because it's the same foreground job, right? You can use the command get process group to get the process group of the current process. You can also set the process group ID to set or change the group ID of the process that you're running. And to send the signal, right, you can, for example, you want to send signal to a process. You can use this queue program, the command queue in Linux. You send an arbitrary signal to a process or a process group. Example is this: if you do process Q-9 with the number, send signal to the process ID 24818. If you have a dash, if you have a dash here, if you have a dash in front of the number, that sends you to the group. Basically, then signal gets sent to every process in that group. Every process in that group. When you type Control C, it basically sends a SIGINT or SIGSTOP. Basically, stop the process. It's almost like a queue, right? Stop the process from running to every job in the foreground group. So when you do Control C, right, everything that has the same group ID as the foreground job will be terminated. SIGINT, the default action of SIGINT, which is Control C, will terminate. SIGSTOP, Control C will stop and suspend the process. You can resume later. So Control C Charlie and C Zebra is different, right? One of them is terminating, the other one is stopping. And you can send the signal inside the program with the queue function. Int gonna be useful for your lab because you cannot write. This allows you to do that inside your program. Then queue, right? With the process ID as an input. Queue command inside the C language takes the process ID and the signal you want to send. So in this case, you can send SIGINT to the process ID that you want to kill. You can also receive this, like let's say a kernel is returning from an exception handler and it's now ready to pass control to process P. Kernel is handling some exception. Now the process P is ready to run. The kernel will compute the PNB as a variable that will equal to pending non-block signal. Again, non-block signal that are pending, right? Basically, any pending signal that you're not blocking. If PNB equals 0, P can run because no one is signaling anything. If PNB is 0, means that there's no signal pending right now. I can run process P. If there's any signal that are pending, based on the signal ID, you need to trigger action based on that signal. And you do this until there's no more signal that has to be handled. So the question you have, what if there's multiple signals, right? In that case, I'll keep handling each one of them until either I terminate, like that process P terminate, or there's no more signal to handle. So each signal will have some predefined default action. For example, SIGINT or SIGQ means that I will terminate the process. Sometimes the default action is terminate and then dump the core content so that I can debug them later if I want to. I can stop until I restart by another signal called SIGCON. So you have SIGSTOP, right? And then SIGCON SIG. Stop will stop the process, continue, basically continue running the process. Or I can ignore the signal. Like if I don't know what to do with this particular signal. To use the handler in C, you can do it this way, right? I write a function called enable signal handler that includes a struct called sig action. That is a struct that relates signal that and an action that I have to do. I will set the handler. So here SA, which is sig action dot SA underscore handler, takes in a function, then you can assign the handler. In this case, it doesn't really do anything except set that variable to true, but you can add more. Basically, it's like your handler. You can do whatever you want in that function to handle the signal, right? Now, when you do SA underscore handler, you set that if you got this signal, go to that function. You can also set the flag. Then, right, you can then call empty set with the sig action as an address with the mask to make sure that you are basically handling that signal. Then you take an action. Yes. What? The empty set. I think it might be better to just check it out on the API. All right, so let's do that. All right, so we're on the man page. So sig empty set takes in the signal and empty the signal. It empty the signal. Say, hey, I handle that, clear it out. Then I perform, in this case, I do another action, which in this case, send a sig int. All right, I handle the, like in this case, I got a signal. I call the signal handler, and in this case, it's a sig int handler. Right, it's in, again, the name is sig int handler. So I first empty the set. Then I set that I will handle the sig int that I get with the sig action that I now set. So instead of terminating, I'll call the handler. Again, the step is first I set the function that says, hey, this is my handler. Then I empty the signal for my process. And I say, hey, because I got the sig int signal, right? I take the action sig int with the new handler that I assign. All right. That's it. Now that's how you can handle the signal. So that we have activity with the signal, activity 4. Wait, 3 or 4. I think it should be 4. All right, this is class 4, activity 4. Quick announcement, GitHub Classroom is updated. I'm sorry about that. I spawned from the last year and I forgot to update the link. Lab 1 deadline, we should talk about this. So let me pause the recording. Actually, let me put it on the recording. How many people want to do it 1 week after we do the first module exam? Lab 1. 1 week after we are done with this whole module. But right now it's on the end of the module, which is kind of like not fair, but that's the exam as well. So let's do it 1 more week. Is that okay?
Yeah.
Cool. All right, in the recording, all right, folks.